Thanks. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. Thank you again for these students. Just pray to be with us today. Help us to glorify you, Lord, in what we do. And I just pray, Lord, that you be glorified in the lives of these students this week and this semester as they work on this course. That just give them the courage to persevere in the face of difficulty, Lord. In your name I pray. Amen. So let me just talk through a couple things before I take your questions about homework. So that's what we're going to do today. To start with, we'll talk about homework a little bit, and then I'll talk to you about integrals of trig functions. Well, maybe some integration by parts, and then integrals of trig functions. So somebody asked me a question. There's one of your homeworks is about finding the absolute extreme value of a function. So this is the related problem. This is number 27. I asked you to do number 26. So basically, here's the logic. To analyze this function, it's smooth, right? So I can use calculus to analyze the extrema. So first of all, I'll go looking for local minimums and maximums, right? Those have to happen at critical points. So we look for where f prime of x is equal to 0. F prime of x equals to 0 gives me 4 cosh minus 5 sinh equal to 0, which gives me hyperbolic tangents 4/5. All right. And then I take the inverse hyperbolic tangent of both sides. That gives me x is equal to inverse hyperbolic tangent of 4/5. But there's this lovely formula that says that's 1/2 the natural log of 1 plus x over 1 minus x with x equal to 4/5. And you simplify that, and you get to natural log of 3, which is pretty nice. And then all I got to do, because this is easy to take the second derivative for, I might as well just differentiate again, and then I can use the second derivative test to figure out if natural log of 3 is a min or a max, right? So the second derivative of f is 4 sinh minus 5 cosh. In fact, the second derivative of f of x is actually equal to f of x itself, right? It's kind of funny, right? You notice that y prime prime minus y equals to 0. This differential equation has solutions of sinh and cosh, by the way. There's a bonus comment for you. Moving back to the problem, second derivative evaluated at the critical point gives me this. Now, so I'm using the definition of sinh and cosh in terms of exponentials. Properties of log says minus natural log of 3 is natural log of 1/3. So the exponential of minus ln of 3 is 1/3. Likewise over here, but plus because it's cosh. And you simplify, and if I didn't do something wrong, I got minus 3 for the value of the second derivative, which incidentally is the value of the function, right? So that's negative, which means that f of ln of 3 is in fact a local maximum. And on the other hand, so that just gives me local data. The question is, what's the absolute extrema, right? So for there, I have to look at the big picture. What happens as x goes to infinity? What happens as x goes to minus infinity? You know. And if you simplify the formula in terms of exponentials, it's really easy to see that this function is non-positive. In fact, it's always negative, right? And as x goes to infinity or x goes to minus infinity, either way, you face minus infinity. In other words, it opens down both ways. And so that local max is in fact a global max in view of this graph. Moreover, no global minimum exists. So there's the sort of analysis that I'm looking for in number 26, sort of a corresponding discussion for that function. This is calculus 1, calculus with graphing, right? Some semblance of these ideas should have been shown to you your last calculus course. Right. Anyway, any questions about this? Okay. The other thing people had questions about last time, and I'm sure you guys have questions about as well, was this problem. I forget the number. Do you guys remember the number? Section 7.9, number 17? Yeah. So the way I see it, there are sort of two lines of attack with this problem. The one I would characterize as brute force. The other one I would characterize as using calculus. So the brute force attack is actually my current solution. I think I'll probably have both in the solution when I post it. I'm not sure. I may or may not forget to put this in there. So the first somewhat unenlightened solution would be something like, okay, so if you're supposed to prove if x squared is greater than or equal to 1, then this inequality follows. So if you look at that, and you break it into cases, what you have is that the absolute value of x squared is greater than or equal to 1, And from that, it follows that the absolute value of x is greater than 1. But absolute value of x greater than 1 gives us two cases. It gives us x is greater than or equal to 1, or x is less than or equal to minus 1. These are the two ways the absolute value of x can be larger than 1. And then the first solution would be just to go and brute force attack this inequality using that through two separate lines of attack, starting with x greater than or equal to 1, or starting with x less than or equal to minus 1. All right, you could do that, just brute force. The other way, and I think this is probably the better way to do it, is to use calculus. So what I do is I define a function, f of x, equal to x minus 1 minus the square root of x squared minus 1. That's an interesting function because that function, being non-positive, being less than or equal to 0, is equivalent to the given inequality we're trying to prove. Right? To say that x minus 1 minus the square root of x squared minus 1 is less than or equal to 0 is entirely equivalent to saying that x minus the square root of x squared minus 1 is less than or equal to 1. Are you guys on board with that? So one of the things I wanted to do the first day when the Donald interrupted us was to remind you we can solve quadratic inequalities in a certain way. Like, for example, if I wanted to solve x squared, plus 6x plus 5 greater than 0. What I would do is I would go, okay, so that's x plus 1 times x plus 5 greater than 0, right? I go, if I look at this as f of x, I have f is continuous on the whole real numbers, right? So I have a continuous function on a connected set. I can apply the intermediate value theorem. And if I draw a sign chart, and if I put on this little tick marks, say at minus 5 and minus 1, then you think about things. For example, could I have a place here where it's positive and where it's negative beyond minus 1? Okay, so what does the intermediate value theorem says? It says that if you pick two values for your function, right, then every other value between those two have to be attained by some number between the inputs to the function. So if I have like f of a, for example, if f of a is positive and f of b is negative, then everything between whatever those values were has to be reached by the continuous function between a and b. So in other words, the intermediate value theorem says that there has to be some 0 between that plus and that minus on that number line. But that's impossible, because by factoring, I already figured out that the zeros are only minus 5 and minus 1, right? So polynomials are very boring. They can only change signs at their zeros because they're continuous. And so we can make a sign chart for this. We can go, okay, so just plug in a point, right? And you'll find that the function's positive here, it's negative in here. And this completely characterizes where the function's positive and negative by the intermediate value theorem. So then I can just read the solution to the inequality. Thus, x squared plus 6x plus 5 greater than 0 has solution in terms of interval notation. It has solution minus infinity to minus 5 unioned with minus 1 to infinity. So there's the solution to that inequality, that quadratic inequality. And I didn't have to break up into cases because I could use continuity in the intermediate value theorem, aided by this notational device of a sign chart to guide my thinking. Similar arguments can be made for rational functions if we take account into its zeros and its vertical asymptotes and the holes in the graph, I suppose. Okay, so this is background. Hopefully you saw this in like college algebra or something, but or something like it. Maybe you made a table with pluses and minuses, right? And you put like little pluses and minuses and you organized your thinking like that. This is entirely equivalent to that table you made with pluses and minuses, all right? So I'm trying to do the same thing here. Because this function, f, well, it's not continuous on the reals, right? Its domain actually is just to the left or to the right of 1 and minus 1. But on each branch here, it's continuous, right? So the only place it can change from plus to minus is at a 0. So what I got to do is find all the zeros for f of x, I put them on the number line, I can completely solve the inequality f of x less than or equal to 0. Do you guys understand the solution technique? Does that make sense? I'm modeling the idea of this to a more complicated function, but. So what do we have to do? You have to find where is f of x equal to 0, right? The solution's not complete. I just started it. You guys got to finish it. So f of x equals to 0 means this is equal to 0, which means you can isolate the radical. Then what's the next step algebraically? Once you're to here. Square both sides, right? And then you factor. And when you do that, when you work out the algebra, you should find that the only 0 of this function is in fact just x equals to 1. So, in fact, the only sort of tick mark I would have to put is here. So then all you got to do is test a point over here and test a point over there to find out whether it's positive or negative. And when you do that, you should find out that this function is never positive. It's usually negative. The only place it's 0 is in fact at 1. But that is a solution to the problem. That would be my advice on how to do this one. Use calculus. Specifically, use the intermediate value theorem. Okay, so this is the higher end of Calculus 1, right? This is the part that you may not have seen exposited too much in your Calculus 1, which is unfortunate, because it's one of the more important aspects of Calculus 1, is that it allows us to come to terms with how big or how small a given continuous function can be. We're going to need these ideas to come up with estimates for things in this course as we go on, right? For example, we'll look at something called a Taylor polynomial. In order to show that this Taylor polynomial approximates a function to a certain accuracy, we'll need to be able to say, like, maybe the third derivative is smaller than a specific number. But that will a lot of times boil down to solving some kind of like quadratic inequality or something, right? So these kinds of inequality problems we will face as we address specific questions about, estimation in here. All right, I think that's all I've got for solutions from the last class, but I guess you guys probably have these questions as well. I will now open up the floor. Other questions? Yes, sir.
7.7 number 32.
7.7 number 32. Oh, we talked about this last week, so I'd rather not talk about it again. Is there a specific question you have about that one?
The whole problem.
Well, you have x divided by the square root of c squared minus x squared, right? So you can use the quotient rule for the first term. Then the second piece, you've got inverse sine of x over c, so you just do the chain rule. So the first, I don't want to erase that. Inverse sine of x over c. Let's talk about that piece. The way to do that is that's basically, 1 over the square root of 1 minus x squared over c squared times the derivative with respect to x of x over c, right? So this is the chain rule. And we also proved last week, right, that ddu of inverse sine of u would be 1 over the square root of 1 minus u squared. So we worked that out from implicit differentiation and some little arguments. But anyway, basically what you have then is you've got 1 over c times the square root of 1 minus x squared over c squared, right? And then you can bring the c inside because c is positive. So this is really c squared minus x squared, since c times the square root of stuff is equal to the square root of c squared times the stuff, because we were given that c is greater than 0. So I can do that. And that's pretty nice, because when you differentiate the first term in that problem, by the quotient rule, right? The other one was what, x over the square root of c squared minus x squared? So think of this as like f over g. So f over g, the derivative of that is f prime g minus f g prime over g squared. And that's pretty much it. Just add them together and see if you can simplify. I mean, when we say c is greater than 0, it should be understood, guys, that when he says something like c greater than 0 in the homework, tied to that is the idea that c is a constant. All right. If he wanted c to be a variable, he would say something else. So c being a constant with respect to x just means that c dx is equal to 0. So we can just pull it outside the differentiations. That's pretty good. All right, I think I've said what I will say about that problem. Are there other questions? Yeah. Was that also your question? 8.2, number 28?
I didn't get there yet.
Oh, okay.
I want to go over some aspects of problems to make my board right. Because I guess my main question is, you always have to, you do it by parts. I mean, it doesn't by parts, integral by parts. You always have to find the integral again for the equations to work all the time.
Well, you know, sometimes integration by parts, right? So sometimes they loop back where they started. Oh, here, now I can erase all this. It's good. So the gentleman just asked me about the integral of e to the 3x times the cosine of 2x. Right? Let me work a similar but different problem, okay? How about this? Integral of e to the 7x cosine of, I don't know, 3x dx, all right? The way these work is we integrate by parts twice. It'll work out. Now, it doesn't really matter if you make this your dv or if you make this, I mean, whatever. There's two choices for u and v which will work here. This problem is somewhat forgiving in that sense. So u is equal to e to the 7x du, 7e to the 7x dx, dv, cosine of 3x dx. So the integral is v is 1/3 sine of 3x. So if you're missing the 7, or if you're missing the 1/3, you're going to go wrong, all right? So we have uv minus the integral of v du. This is integration by parts formula. So in particular, that gives me 1/3 e to the 7x sine of 3x minus the integral of 1/3 e to the 1/3 times 7 e to the 7x. I got my sine of 3x in here, dx. Let me just clean that up before I go on. 1/3 e to the 7x sine of 3x minus 7/3 integral of e to the 7x sine of 3x dx. Now, you're like, well, that wasn't that helpful. That's just something else I don't know how to integrate. True, but it's different, right? And there's a light at the end of the tunnel, and it's not a train. It's okay. It's safe. So this is a very old joke. I don't know if it shouldn't get so much mileage in your eyes here. U2. So you just do it again. And so this time, u2 e to the 7x, so du2, 7 e to the 7x dx. V dv2 sine 3x dx. So I integrate, I get v2, be careful, minus 1/3 cosine of 3x. Right? By u substitution there. And so what I have then is I've got 1/3 e to the 7x sine of 3x minus 7/3, and let me put some parentheses here. So what I'm going to write now is u2 v2, which is minus 1/3 e to the 7x cosine 3x minus the integral of v2 du, which is going to be plus the integral of 7/3 e to the 7x cosine 3x dx. Again, what I put in parentheses here is exactly just u2 v2 minus the integral of v2 du2, right? That's what's inside the parentheses. Now be careful. The parentheses are your friends. Neglect them to your own peril. 1/3 e to the 7x sine 3x. That's usually the sort of error, sort of comment I made right before I make a horrible mistake based on not appreciating parentheses. Let's see here, 7/9. E to the 7x cosine of 3x. So I've got myself a minus 49 over 9. 7 times 7 is 49. 3 times 3 is 9. Integral of e to the 7x cosine of 3x dx. At which point, I'm happy, because I'm just about done. You see, if you call this thing I for integral, then what we have over here is the same thing again, right? This is I. More specifically, if I collect the term in front of it, I've got minus 49 over 9i, right? So if you'll allow me a little notation here, let me call this thing Pac-Man. So what we've got is that I plus 49 over 9i is equal to Pac-Man. If I just add that to the other side. Pac-Man, we know, just a function. So divide what 49 plus, what's this? This is otherwise known as what? 58 over 9, right? Do you agree, disagree? I mean, if I made a mistake here, I'd like to know about it. Now, as opposed to like 2 minutes from now. Everybody follow along? Yes, sir.
Would you go ahead and carry over the 59 over 9 to Pac-Man? Or would you just...
58 over 9, but oh yeah, I'm not done yet. I'm just before I get conclusion. Therefore, the integral I, which of course is the integral of e to the 7x cosine of 3x dx, is equal to 9/58 times e to the 7x. Oh, sorry. 1/3. I mean, you could simplify this a little bit further. I'm just not, because I want you to see what I did. Sine of 3x plus 7/9 e to the 7x cosine of 3x. And then plus a constant, because we were doing indefinite integration. There you go. What's the relation between 58 and the numbers which are given? How do 7 and 3 and 58 relate? Seven squared plus 3 squared is what? That is not an accident. It's not an accident. In your problem, you have 4 and 3. No, you have 2 and 3 in the problem in the homework. And for essentially the same algebraic reasons, you'll end up with division by 13. Because 2 squared is 4 and 3 squared is 9. And 9 plus 4 is 13. So essentially because we integrate twice and differentiate twice. Each time we differentiate or integrate, we pull out a factor of 2 or 3 in your problem, or 3 or 7 in my problem. So we can kind of expect that there's going to be a division by 58 in this problem or 13 in your problem when you work it out correctly. Yeah, but this is another, this happens a lot with integration by parts. You loop back where you started, but not quite where you started, and then you can do algebra to solve for the integral. This is a common type of example. Next. Oh, sorry. Too early? You guys just want to be out sledding? I mean, what is it? Yes, sir. Oh, sorry, there's... Ah, yes. I know what the problem is with that one for you guys. I'll show you. I worked that one earlier today. The problem with that one probably is you don't know how to integrate x squared divided by x plus 1, right? I repeat that. You do not know how to integrate x squared over x plus 1. Correct? Yeah. Oh. Here's how to use integration by parts to get integral of cosine squared theta. I'm going to leave that there for later because I'm getting tired of writing, if you don't mind. It's a perk of teaching the same class twice in the same room. Sorry. Okay, so what was it? Is integral of x ln of x plus 1? Is that right? All right, so you're right to start with. So Liate, if we believe, says that should be u. And then this thing should be dv, right? So that gives me 1/2 x squared times the natural log of x plus 1 minus the integral of v du, which would be 1/2 x squared times dx over x plus 1. All right. Are we good on that? I mean, u. So here's the integration by parts thought bubble. All right. Now, the thing that's kind of a drag here, and I'll just focus on this piece that you're stuck on, is how on earth do you integrate something like x squared over x plus 1? If you don't mind, I'm going to ignore that half and just focus in on this, if that's all right with you guys. How do you do that? Okay. So u substitution will probably work. That's true. That's not bad. You guys are just like, let u equal x plus 1, and then you can do it.
When I tried using u substitution, I started moving back around.
No. U equals x plus 1. Du is equal to dx. So then x is equal to, here's the thing you maybe didn't do, u minus 1. You have to do that. If you don't do that step, you don't know what you're doing. I mean, no offense, but it's true. Equals. I mean, good grief. If you guys already knew everything, there would hardly be a point in taking the class, right? I mean, if you're ever in a class where you're not hearing anything you haven't heard before, you probably should drop it, you know? What's the point in paying money to learn things you already know? Let's see here. U minus 1 squared is x, right? And then I divide by u. Dx is du. And then this is u squared minus 2u plus 1 divided by u du, which is the integral of u minus 2 plus 1 over u du, which is 1/2 u squared minus 2u plus the natural log of the absolute value of u plus a constant. In other words, 1/2 x plus 1 quantity squared minus twice x plus 1 plus the natural log of the absolute value of x plus 1 plus a constant. So, hey, Actually, that's pretty nice. That's not what I did earlier today. But that is a legit way of doing that integral. Sure. Yes, sir.
About this problem, you had the 1/2 x squared dx over x plus 1. Where did the 1/2 go? In that
I'm just talking about how to integrate everything except for the half.
Oh, you are.
Yeah. Yeah. So that's on purpose. I just don't want to carry the half through here. You have to take this and add some thinking to get to the answer, right? Now, there's another way to look at this problem, which I think is useful, and it's part of a larger discussion, which is how do you integrate? I mean, there's precious few times I can complete this sentence. You can integrate any function of the form blah. Now, there's a couple of very special kinds of classes of functions where I can just do that. For example, any power of sine or cosine we can integrate. That's really nice. It's not usually the case that we can do that. It's also the case, and this is a more difficult thing to establish, you can integrate any rational function. You give me a rational function, which is just the quotient of two polynomials. There's an integral for that in terms of elementary functions. So that's pretty nice. This is one of the rudimentary examples that you'd face in the study of such a question. So we've got like x squared over x plus 1, right? This is actually an improper rational function because the numerator has larger degree than the denominator. So how do you simplify this? Well, there's a couple different ways to do it. I'll show you the long division way for now. Earlier today I added 0, but since we did another thing here, I won't do it now. Let's see here. So I'm dividing x plus 1 into x squared, right? So x, subtract, I get minus x. So how do I get minus x from this? Minus 1. All right. And so we have a remainder of 1. What this tells me is that x squared divided by x plus 1 is equal to x minus 1 plus 1 over x plus 1. Which means that I can integrate x squared over x plus 1 dx as simply 1/2 x minus 1 quantity squared plus the natural log of the absolute value of x plus 1 plus a constant, and I'm done. This is not wrong. There are different ways to do it. But long division is helpful to simplify a rational function into its more a polynomial plus a proper rational function. Later this week, we'll talk about how to integrate pretty much arbitrary proper rational functions. Yes, sir?
Okay, so when you do the derivative, not derivative, when you find the integral again, like we just did on that board, you don't always have to do IBP again. You can just do it just like that. That's how you got it correct.
Yes, to solve integrals, it's kind of like putting together a house. Use a hammer, maybe use a nail gun some places. Other places you use one of those things you carry the drywall with. Other places you put plaster on. Other places you look at the plan. There's like lots and lots of different tools that you use to make a house, and same with integration. Like integration by parts is just one of our tools. But actually solve an integral, we don't have to stick with just one method. There's lots of different methods. They work together in concert to solve a problem. So yeah, I started with integration by parts, but I finished with something rather different. And even there I had options, right? Your U substitution, my long division. There's still U substitution here. I integrated this by making a U equals x minus 1 substitution, and I integrated this by making a U equals x plus 1 substitution. I just didn't write them down. There must be another question about this homework. Yes? Yes, sir? Right. Now, so you're supposed to prove that cosh x plus sinh x to the nth power is equal to cosh nx sinh nx. So let me just give you a hint. Two things we know. E to the s raised to the t power is equal to what? E to the st, right? It's a law of exponents. First hint. My second hint to you is that cosh x plus sinh x is equal to e to the x. And section 7.8, number 29? Is that right? 29?
Yeah.
Okay. So I originally assigned this problem because I wanted to have a chance to talk to you guys about induction. But after the dust settled, I realized this is not an induction problem. This is just a stone-cold algebraic manipulation problem. You take those two hints, you put them together, done. If I write any more, I've solved the problem, almost. Dwell on these things, yeah. Next. Yes, sir. 8.2, number 34. All right. Cosine of the square root of x. All right, so if only I could think of a similar problem which I could work, which wouldn't be exactly the same problem. How about sine of the square root of x? That should be the same, but different. Now, what's the hint?
That u equal to the square root of x and ab should be cosine square root of x over square root of x.
So he's like, let u equal the square root of x?
Yeah.
All right. So that makes, this is kind of funny. Du is dx over twice square root of x, right? Now, it requires a little imagination. Let me write one more step here. So this is the integral of the square root of x, right, times the sine of the square root of x divided by the square root of x dx. So that's the hint this, as it applies to this problem. And so the point of that was he's going to, it's kind of sneaky, right? I multiplied by 1 here, right? Divide and multiply by square root of x. Sneaky step. So this is the u, and this is the dv. So dv is sine of root x divided by root x. So that means v is equal to minus the cosine of the square root of x. Is that quite right? If we differentiate cosine, we get minus sine, right? And then we have to multiply by the derivative of the inside function, which is square root of x. Derivative of square root of x is 1 over twice square root of x. There's an extra 2 I don't want. So multiply by 2. Now they cancel. In other words, the integral of this is that. I just ran out of board space, so I'm just doing it in my head. That's okay. Well, even if it's not okay, I've already done it, so sorry. But equals. So again, as usual, uv minus the integral of v to u. And so this boils down to what here? So square root of x. Oh, sorry. Let me bring the minus 2. So minus 2 square root of x cosine of the square root of x plus 2 times the integral of cosine of the square root of x. And then what's my du? Dx over 2 square root of x, right? Aha! So again, I have got like cosine of root x over root x. Well, that's nice because that's a u substitution. Or maybe let me say a w substitution, right? Basically. So I got minus 2 square root of x cosine square root of x plus 2 sine of the square root of x plus a constant. Something like that. So the 2's cancel, and I'm left with, I have to integrate. I'll work it out down here. It's like, how do you integrate cosine of the square root of x dx then, right? You say, okay, so w is the square root of x. I'm sorry, I have division by root x. That's important. So w equals root x, dw is dx over twice the square root of x. So this gives me cosine of w cosine of w. And if I solve, so dx over root x is just equal to what? 2 dw. So I do 2 and keep the dw in here, and that gives me 2 sine of w plus a constant. And that's how I got this up here. I also made that same w substitution in my finding v from dv by integration at the start of this. So that's how to carry out the hint. It takes some imagination to see the u and the dv to start with, is the point. Other questions? Yes, sir.
Number 50 on 7.8.
So we have the region below the curve y equals sinh x. From x equals 0 to x equals natural log of 5 is revolved around the x-axis. Find the volume of the resulting solid. X-axis, all right. So let's see here. Sinh x looks like this. From 0 to natural log of 5, roughly speaking, right? And then we're rotating that thing around the x-axis, right?
Yeah.
So it's kind of like some kind of like horn-looking thing. And so a typical cross-section in here would be a disk, right? Something like this. And so the thickness of the disk would be dx, and the area of the disk would be pi times the hyperbolic sine of x quantity squared. See, because this is y equals sinh x, right? Okay, so if that's the area, that's the thickness, the infinitesimal volume from that little slice would be pi hyperbolic sine quantity squared times dx. And so you see, to find the volume, all I have to do is add the volume of each little disk up as we go from 0 all the way out to x equals to 5, right? This is for 0 less than or equal to x less than or equal to ln of 5. So all I got to do is integrate from 0 to ln of 5 of pi times the hyperbolic sine squared of x dx. There you have it. Now, is your question how to integrate hyperbolic sine squared, or this is the setup? Yeah. Yeah. Did we work out the identity? I'm trying to remember hyperbolic sinh squared. It can be simplified in terms of like cosh's or sinh of a single argument. So there's something analogous. I mean, sine squared theta simplifies to what? Right? There's something similar for hyperbolic sine. It's in the book. I don't remember off the top of my head. On page, uno momento, I will tell you. There's a box of goodies on page 390. It doesn't quite do it for us, does it, though? Well, I don't know. There's various ways of deriving this. We could. Oh yeah, yeah. You could if you go back to integrals of exponentials, you could do it that way. That'd be fine. Yeah, well, I'll leave this integral to you. There's various ways to think about it, but I will write a solution to the homework. You can look at my solution there. In the meantime, I'll leave it to you guys. Other questions? I think this is the hard part, right? If you haven't seen that before. Yep. So number 14, my big hint to you is to first figure out what is sinh of a plus b and figure out what cosh of a plus b is, right? Figure out those two identities and then just divide them and follow the same thing we did for tangent, for hyperbolic tangent, and you'll get it, right? So that'd be my hint there. Do something like this. And the identity for sinh and cosh, it's almost the same as the cosine and sine, but not the same. I just had it a second ago. That box, where was it? So if you look on page 390, you can see what you should be able to derive. So just, I mean, it might be good for you to work these out for that homework problem, right?
I got that far.
Oh.
It's just getting it down to the tangent looks going to be over 1 part.
Okay, so what you want to, if you've already got the sinh identity over the cosh identity, you want to divide by cosh A, cosh B, the top and the bottom. That'll put a 1 downstairs and produce tanh, and then product of tanges on the bottom. Divide by the product of hyperbolic cosine, A and hyperbolic cosine. Were they S and T? Yeah, S, hyperbolic cosine S and T. So it's almost the same as what we did in class for tangent. You know, there's just like a SIGN difference. But yes, sir.
I have a question on the cosh identity for the sum. Why is the slightly sine different than the cosine for this formula?
Well, one way to see that is if you take the sinh identity, which is sinh cosh plus cosh sinh, right? Let me say x plus a. So sinh x cosh a plus cosh x sinh a. One way to understand that is you can differentiate the sinh identity to get the cosh identity. Derivative of sinh is cosh, no minus. And likewise down here, so if I differentiate this, I get, with respect to x, I get cosh x, cosh a, plus plus sinh x, sinh a, right? So if I erase the h's from the upper identity, that's true for sine. But when I differentiate that, the second term obtains a minus because derivative of cosine is minus sine. And that's one way to understand the difference. You could see it as coming from I squared being minus 1, but there's like an I in the imaginary exponentials for sine and cosine, but there's not for the hyperbolic sine and hyperbolic cosine. There's a lot of different explanations you could give as to why they're different, but yeah.
Just a quick question. On our subsequent number 29, we already kind of like went through one way to do it. What I did was that, like, because it said like show that this is equal to this, I set it equal, like if they're equal, and then I went and like did algebra to both sides.
Well, I would prefer that we don't do that. I think that's taught in high school sometimes, but I think it's really, really a wrong practice. It gives the instructor the idea that you're assuming what you're trying to prove at the outset. So when we're trying to prove something's equal to something else, we should start on the left-hand side and do allowed algebraic expressions until we reach the right-hand side. Okay. Something like that. Like saying A equals B and then doing stuff and then it's still true. It begs the question, how did you put A equals to B to start with? Yeah, I'm afraid certain high school algebra and geometry texts are especially guilty of this, and it's rather unfortunate. Yeah.
Would a way around that be to assume that they're not equal to each other and show it doesn't work?
No, because if they're not equal, I mean, I don't think that. just essentially make the same steps you made, just pick a side, and then do those things and get to the other side. Don't start by assuming A equals B. A equals what it is, do an allowed operation, step 2, allowed operation, step 3, step 4, the nth step, or whatever step it is you get to the right-hand side, then you've shown that starting with the left-hand side, you get to the right-hand side by, allowed steps of algebra and calculus, whatever. Yeah. The sine root x? Not that I know of, right off the top of my head. I mean, probably. I'm just following the hint the book gave. I mean, what else are you going to do to start with? You got sine of the square root of x. What can you make u? Yeah. I mean, I suppose an alternative way to attack this would have been something along the lines of, so I'm faced with the integral of sine of the square root of x dx, right? And so what I would just do is say, let w equal to the square root of x, right? If I do that, dw is 1 over twice square root of x dx, right? In other words, it's dx over 2w. So this is actually the integral of sine of w times 2w dw, because dx is 2w dw. And so lo and behold, I've got the integral of w sine of w dw times 2. And if you remember last class, pretty much any time, this is something I haven't done enough of, but if we have the integral of x times some function we know how to integrate, integration by parts will fix this. Pretty much. All right, so like this, I would just let this be my dv. I would let this be u. And so like u is equal to w. dv is sine w dw. So du is dw. V is equal to minus cosine of w. So this is 2 times uv minus integral of v du by the integration by parts formula, which is 2 times minus w cosine of w minus the integral of, well, plus, right? Because the minus and minus gives me plus. Cosine of w dw. But, of course, the integral of cosine is sine. So I get minus 2w cosine of w plus 2 sine w plus a constant. In other words, I get minus 2 square root of x cosine of the square root of x plus 2 times the sine of the square root of x plus a constant. Now, why didn't the book tell you to do it this way? I don't know. Could have. The awkwardness, of course, is that I have to do integration by parts in a variable other than x. But you can do that. I'm sure there's another way to do this. Yeah.
That's totally fine, but I mean, the only thing that got me confused was square root of x times sine square root of x plus square root of x. I didn't understand that.
Well, I mean, the point is that in order to make u and dv a reasonable choice, I have to be able to integrate the dv. If I try to make v, I mean, what are my choices here? I can make u equal to the sine of the square root of x. Then I can calculate du, great, right? And I can make the dv dx. But the next step then I would get would be like x times the cosine of the square root of x divided by the square root of x, which you might be able to integrate if you simplified still. I mean, there's other ways to do it. I mean, probably that would also work, actually. If you realize that x over the square root of x is, in fact, I don't know. We've solved it 2 ways. That's enough. Let me shut up about this problem. Other questions? Yes, sir.
For 7.48, would you recommend that we
Yeah, I think the best answer here is given in terms of there shouldn't be a cost or a natural log in the answer. You can give it in terms of exact fractions or something like that, yeah. Hyperbolic cosine is positive, right? So if you're finding the area below it from a to b, it's just straight up the integral from a to b. It's not, there's no negatives to worry about, right? To find the area under the curve, I just integrate from a to b. So I just got to integrate hyperbolic cosine of 2x from minus the natural log of 5 to the natural log of 5. I guess if I want to be lazy, this is an even function, so I could just double the integral from 0 to natural log of 5 if I was so inclined. But yeah. But I erased it. But remember earlier at the start of class, I did stuff like I plugged in natural log of 3 into the sinh. So that kind of simplification you need to do there. Yeah. Other questions? All right, so it's good. I try to give you more examples before you ask homework questions about something. We just kind of lost today, so I ended up having questions about the integration by parts at the same time. Most of the questions I've answered here were integration by parts, right? So I would like to have had a lecture where we did that before you asked the questions about your homework. It's just, the details of the semester haven't made that happen. I'm sorry about that. And as much as I'd like to post a video to get us up to speed, this particular part of the course really needs to be done in person, because you need to be able to ask questions about what I'm doing as I go. There's some things we do later, like if we lost a snow day on certain topics, it wouldn't break my heart to post a lecture for you on YouTube or whatever, but this here, you need to be able to interrupt me and say, why did you do that? It's really important. So that's why I didn't post lectures in the snow days. I don't really guess I need to justify why I didn't do that. You're probably fine with that, but yeah, it's unacceptable. I saw you posted a lecture for linear algebra. Why didn't you do it for us? No, that's not how you think. It's not fair. In my house, you're allowed to say stupid, but you're not allowed to say it's not fair. It's our house rules. My wife is pretty dogmatic about if the children say it's not fair, she will start listing all the things she does that they don't do. It's not fair that you don't wash your clothes. It's not fair that she has a long list. I'm not as well prepared for these kinds of arguments with children. An argument with their mother is an argument they will never win. Oh, okay, so our topic for the remainder of today, how much time do I have? The time so far was not wasted. I think it's important for you guys to be able to ask questions about the homework. But we got, 17 minutes for class end at 11, is that right? All right. So earlier, I did some fun stuff. Well, not really fun. I showed you how you could try to use integration by parts to derive the integral of cosine squared. Let me just tell you what we're doing. We're now trying to figure out what are the integrals of trig functions. This is not to be confused with trig substitution. That is something else. Soon, but not today. So I'll start out with the basics. Integral of cosine theta, integral of sine theta, integral of tangent theta. These we know. Integral of cosine is sine theta plus a constant. Integral of sine theta minus cosine theta plus a constant. Integral of tangent. Let's use our sneaky notation. This is sine theta d theta divided by cosine theta, so that's really minus the derivative of cosine theta over cosine theta. So we get just what you guys just told me, minus the natural log of the absolute value of cosine theta.